Hello friends, everyone. My name is Javin Nunisa from Assam Don Bosco University, and my topic today is fiber fabrication. So, what is fiber fabrication? Fiber fabrication is basically how a fiber is made. There's a wide range of methods for fiber fabrication of optical fibers. In the first step, this can be divided into methods involving a so-called preform and methods of direct fiber production. Preform based methods are most important, at least in the context of glass fibers, whereas direct methods, example based on extrusion, are common for plastic optical fibers. Now, methods. Basically, here we see two methods. One is called preform and the other one is called direct fiber production. Now, what actually happens in a preform? A fiber pulling from a preform. Most glass fibers are fabricated by pulling from a so-called preform in a fiber drawing tower, an apparatus which is typically several meters high. The preform is a glass rod with a diameter between about 1 and 10 centimeter and roughly 1 meter length. Along its axis, the preform contains a region with increased refractive index which will form the fiber core. When the preform is heated close to the melting point in a furnace, at the top of the drawing tower, a thin fiber can be pulled out of the bottom of the preform. The fiber from a single preform can be many kilometers long. During the pulling process, the fiber diameter is held constant by automatically adjusting the pulling speed with an automatic feedback system. Fiber pulling works quite well for the usual silica fibers. Since silica has a rather broad glass transition, there is a large range of temperatures in which the viscosity is in a suitable range. Other materials, as used example for fluoride fibers, have a much smaller temperature range suitable for pulling, and the metal is accordingly more delicate. Fabrication of fiber preform. Uh, Fabrication of fiber preform is basically vapor deposition methods. Many fiber preforms are fabricated with a process called modified chemical vapor disposition, MCVD or just CVD. Chemical reaction in the gas form a line suit of silica which coats the inner surface of the glass tube near the burner and is sintered into a clear glass layer. The burner is continuously moved back and forth along the tube. Towards the end of the process, the gas mixture is modified to form a layer with higher refractive index, the precursor of the fiber core. Finally, the tube is collapsed by heating it to 2000 degrees Celsius. Now, various alternative vapor deposition methods have been developed, and the first one is called outside vapor deposition. Now, what happens exactly in outside vapor deposition is that the silica soot is deposited on the surface of some target rod rather than inside a tube, as with MCVD. Together with the material precursors such as silica chloride, a fuel gas such as hydrogen or methane is supplied to a burner, which is again moved along the rotating rod. After the deposition, the target rod is removed and the preform is consolidated in a furnace where it is also purged with a drying gas for lowering the hydroxyl content. Now, the next one is called vapor phase axial deposition, also known as VAD or AVD. Now, what happened here is that it uses a modified geometry where deposition occurs at the end of the target rod. The rod is continuously pulled away from the burner and very long preforms can be made. Consolidations of the material can be done in a separate zone melting process. Now, the next method is known as plasma chemical vapor deposition. Here, it uses deposition inside a tube similar to MCVD. However, microwaves instead of a burner are used for heating the deposition region. The deposition is slow but very precise. A modified method with particularly high precision is plasma impulse chemical vapor deposition, PICVD, where short microwave pulses are used. There is also plasma enhanced chemical vapor deposition, PECVD, operating at atmospheric pressure with fairly high deposition rate. The preforms for multimode fibers, particularly for large core fibers, are often fabricated using plasma outside deposition, where an outer fluorine doped layer with depressed refractive index later forming the fiber cladding is made with a plasma torch. The core can be made of pure silica without any doping. Methods without vapor deposition. For materials where vapor deposition cannot be applied, the rod in tube technique is another option. Here, a rod of a glass with high refractive index is inserted into a glass tube with lower refractive index. Both can be reasonably well connected by heating, but a great care is required to avoid bubbles and other disturbance. There are also casting methods where molten core glass is poured into the cladding or sucked into the tube using a vacuum pump. Preforms for photonic crystal fibers contain small holes throughout, are usually fabricated by stacking capillaries tubes or rods, in most cases made of pure fused silica. It is possible, of course, to introduce rare earth doped rods for active fiber devices. Now, adaptive methods for active fibers. Now, for active fibers devices such as fiber lasers and fiber amplifiers, rare earth doped fibers are required. Here the fiber core is doped with rare earth ions, example of erbium, neodymium, ytterbium or thulium. Additional dopants can modify the refractive index, improve the solubility for rare earth ions, or modify the photosensitivity. Not all dopants can be easily incorporated with vapor deposition methods, requiring convective material transport. In particular, precursors for rare earth dopants usually have a too low vapor pressure. One possibility to overcome this process is to expose the source of rare earth ions to a higher temperature. For example, a glass tube as used for MCVD may contain an additional dopant chamber or a porous silica pot soaked with a rare earth salt, which is heated with an additional burner. Another common technique is solution doping, where initially a porous silica fluid, not yet containing rare earth ions, is deposited on the inner side of a hollow silica tube. This fluid is then soaked with a solution containing a rare earth salt. Later on, the preform needs to be further processed to form a dry and compact rare earth oxide layer. An alternative technique is direct nanoparticle deposition from some aerosol. This method allows for high doping concentrations with good homogeneity and accurate control of the doping profile. Now, the next is fabrication methods not involving a preform. Soft glass fibers are often fabricated with double crucible method, where the core and cladding are simultaneously drawn from the crucible. The crucible has a reservoir for the molten core glass, leaving a small opening at the center and one reservoir for the cladding glass. The double crucible method is older than the vapor deposition methods and is still used. Example for soft glasses. Compare with drawing from a preform. It can be adapted more easily to different glass materials. However, it is less suitable for producing ultra pure fibers with a very low losses, as it is difficult to avoid any contamination with the materials from the crucible. Some fibers, example plastic optical fibers, are produced in a simple extrusion process which is similar to the double crucible method. Such fibers are interesting for applications in mass markets but do not reach top level performance. Thank you.